As a continuation of our discussion of forces and how forces interact with an object's motion, today we're going to solve one of the most classic Newtonian physics problems that there is, and that is forces on an object on a ramp. In this video, we're going to get to a lot of interactions of forces and really close attention to detail of how forces are oriented, parallel or perpendicular to each other. So there might be times when it's useful to stop and rewind and rewatch certain parts of this, but we're going to go through together here the general idea and then do an example at the end. So today we're going to look at forces on a ramp. To start us off, I want to start with the problem that you all are able to do at this point, because we have talked about this in our other examples. If we know four forces that are acting on a block, and all those forces are either parallel or perpendicular to each other, things will cancel out to give you a net force, and then if you know net force and a mass, you can find an acceleration. So on your own, I would like you to pause and calculate the acceleration of this 10 kilogram block. The only difference here from what we've seen before is now, instead of the forces being perfectly horizontal or perfectly vertical, they're just tilted at an angle, but these 75.1 newtons are still equal and opposite, so they still cancel each other out. So we're left with a 63.1 and an 11.3 that are opposing each other, and they can cancel each other out to give you a net force that's the difference between them, 51.8. If you know the net force is 51.8, and you know that the acceleration is just F net divided by the mass, then you can figure out using the mass of 10, 51.8 divided by 10 gives you an acceleration of 5.18 meters per second squared. Keep this in the back of your mind. We are going to see this picture again, but it's going to take us a few steps before we get there, starting out with the ramp that we're going to see. So we'll come back to this in just a moment. So a couple of big ideas that we've talked about in this unit so far. First, acceleration is zero when net force is zero. If net force is zero, it doesn't mean that it's stopped. It just means it's not accelerating. Accelerating just means a change in velocity. So acceleration of zero leads to a constant velocity. Zero is a constant velocity. So it could mean stopped, but it could also mean your cruise control down the highway at 60 miles per hour, not changing your speed. That's still a net force of zero. The forces cancel, which means you're not speeding up, you're not slowing down. If you do have an acceleration of an object, or you do have a net force, you can calculate the other one using F equals ma, that relationship of Newton's second law. And then if you are trying to find the force of friction, all you need is the normal reaction force, that R, how much the surface is pushing perpendicular on the object, and the coefficient of friction, which is a unitless number defined by the surfaces that are interacting with each other. So if we have an object here sitting on a ramp, we can calculate or determine the direction of several different forces that are acting. First, we can assume that this object has mass, because it's made up of matter. That mass will interact with gravity to create the weight of an object, which is the force of gravity pulling straight down towards the center of the earth. If we have an object on a ramp, gravity doesn't care that the object is sitting on a ramp. It's still going to pull straight down. It's not going to change because of the orientation of the surface that the object is sitting on. But some of the other forces might. If you remember back when we first talked about the normal reaction force, that R value, R can only point perpendicular to the surface that is causing the force. Normal is just a mathematical term that means perpendicular to. So the normal reaction force R, if you are on a ramp, is going to change with that ramp. So the bigger the tilt, the more R tilts along with the ramp, as long as it is perpendicular to the surface. And then our last force that we need to really be paying attention to here is the force of friction. Friction will always oppose the motion of the object, which means this object can really only move up or down the ramp. So depending on the motion of the object, our force of friction will either be up or down, and it'll just oppose that. If we don't have any force that's pulling the object, so like if the example isn't you're pulling this thing up a ramp, then we can assume that the object is moving or attempting to move downward because of the force of gravity. So most cases we're going to see a force of friction pointing up, and that's the friction, just the stickiness of an object to try to stick to the ramp so it doesn't slide down, just holding it up there. It will always oppose motion. Now this picture here is a nice three-force free body diagram, but the problem with this is we can't cancel forces out quite as nicely as we did in the warm-up problem, because this force of gravity isn't parallel or perpendicular to the other two. So before we can do anything, we need to fix this force of gravity to put it in the same orientation as this R and this FF. Because ultimately, this is the picture that we want. We want all forces to be either parallel or perpendicular to each other so that we can easily calculate a net force. So to do that, we're going to have to break this force of gravity down into its components. And in the past videos, we've talked about the components of a vector being the x component and the y component, or the horizontal and the vertical. And that was because we were in a pretty much horizontal plane. Our axis system was based on our environment. But here, if we are tilting our object up, we are experiencing a plane here that is changing in its motion, or changing in its orientation. So now, instead of an x and a y, we are going to break it down into components based on the object itself on this ramp. So we have a force of gravity going down, but then we're going to break it into a component where we have a force parallel. So how much of this downward force is parallel to the ramp, trying to push it down in that direction, and how much of it is perpendicular to the ramp, basically just driving it into the ramp itself. These two forces here can make a right triangle with the force of gravity. So all I'm doing here is I'm just rearranging these to create a right triangle. Now it's very important that you're drawing this correctly. These are our symbols here. We got FG, F perpendicular, and F parallel. But the right angle of this is crucial that you're putting in the right spot. The right angle by definition is the angle between this parallel and this perpendicular line. So that's where your right angle is. It's very easy to draw this kind of wonky so that you put the right angle in the wrong spot, and that screws up your SOHCAHTOA pretty dramatically. So here, if we know that that's the right angle, all we need now is an angle for one of these parts of the triangle. Now, we're usually given the angle of this ramp, or we can find it in some means. So if we know the angle of the ramp, we can use geometry and some geometry proofs to figure out an angle in this triangle. It turns out that the angle here on this part of the ramp is the same as the angle here between FG and F perpendicular. These are just similar triangles with the triangle of the ramp that's shown here. We could do a long geometry proof to figure that out, but right now let's just take our word for it in this case that that angle is the same as the angle of our ramp. Now if we know that the angle here is opposite the force parallel, we can use the sine rule to find the sine of theta is equal to the opposite F parallel divided by the hypotenuse FG. So if I solve for F parallel, I can calculate that coefficient or that component of the force of gravity just by force of gravity times sine of that theta, that angle. Then if you're finding the perpendicular force, we're going to use cosine since that's adjacent to the angle. So the cosine of the angle is F perpendicular divided by the force of gravity, or you could say F perpendicular is just FG times the cosine of theta. We're going to be using that here in just a little bit, but that might be a good thing to have jotted down so that you have access to it later on. That is not going to be in your data booklet for the IB exam, however. So you need to be able to use your understanding of SOHCAHTOA and your understanding of how to draw this triangle to figure it out from there. So let's take note of the forces that we have. Now instead of FG, what we're going to be using now from here on out is F parallel and F perpendicular. So I'll show that again. FG gives way to the parallel and the perpendicular force. These two added together are equivalent to FG, so we're not going to have all three of those forces on our free body diagram, just these two or that one. These two are going to be a lot easier for us to use from here on out. So once you found them, you can forget about FG. That's done its job. You're able to figure out the parallel and the perpendicular force. Now, remember that the normal reaction force, R, is always perpendicular to the surface. And we know that this object is only moving along the surface of the ramp. It's not flying up into space. It's not going into the ramp, which means that this perpendicular force has to perfectly cancel out any force on the opposite side. And we know that that force on the opposite side is R. It's the normal reaction force. So if you know F perpendicular, you also know R. How much that surface is pushing perpendicular to the surface is always going to be equal to the perpendicular force. When we first talked about R, it was usually equal and opposite to the force of gravity, but that was only because we were dealing with a perfectly horizontal surface. And with a perfectly horizontal surface, the force of gravity was going straight down, which was perpendicular to the object. So all of gravity was F perpendicular. So it was still true then. It's just even more true now when that force of gravity isn't necessarily equal and opposite to R. We can also find the force of friction. As I mentioned before, since we don't have some external force pulling it up the ramp, we can assume that the object would naturally slide down. So FF is going to oppose that slide and point up. And you should remember that FF, the force of friction, is related by this equation. Mu times R, the coefficient of friction, times that normal reaction force. And we know R, so we should be able to find FF as well. The hardest part about this is all of these little relationships kind of chain together. There isn't one equation to plug in and solve it all. You need to know how all of these forces interact with each other. Now, one last interaction that is possible is if you find out that this object is either not moving or not accelerating, so it's moving at a constant speed. If that's the case, we know that no acceleration means no net force, and R and F perpendicular are already canceling each other out, which means that FF and F parallel would have to cancel out as well. So if you know that the object is in equilibrium, it's either not moving or it's moving at a constant, these two have to cancel each other out. And we've seen that in old IB exams. This question comes up every once in a while, saying like a wooden block is sliding down an inclined plane at a constant speed. Constant is important. The magnitude of the frictional force between the block and the plane is equal to either 0, B, the magnitude of the weight of the block, C, the magnitude of the component of the weight parallel to the plane, or the magnitude of the component of the normal reaction parallel to the plane. A, B, C, or D, which one of these is the best answer? If we look back at our last slide, we know that if it's in equilibrium, FF is equal to F parallel. And F parallel, if you remember, was just a component of our weight. So our best answer here is C, the magnitude of the component of the weight parallel to the plane. All right, let's put some numbers to this. As I mentioned before, this is like the classic physics problem because there are so many relationships and there are so many variables. Here, this is an example of something that I might give you. I could say that you have a 10 kilogram block sitting on a ramp. The ramp itself, I'll give you some information, is 40 degrees in incline with a surface boundary that gives you a coefficient of friction of 0.15. Remember, that's a unitless number, just talking about how big the friction is relative to R. So if we know the mass, we can find Fg. Ultimately here, I want to know the force or the acceleration of this object as it would slide down, accelerating down the ramp. And believe it or not, these three values is enough to get that. So we're going to start here, kind of plugging our way down here. 10 kilograms can be used to find the weight, just mass times gravity. 10 times 9.81 gives us 98.1 Newton. So we know the force of gravity, and we know that that is straight down. But if you remember, our whole goal in this video has been how can we make everything either parallel to the surface of this ramp or perpendicular? So Fg is not going to be with us for very long. Instead, we care more about these components, F perpendicular, the pink one, and F parallel, the light blue one here. And we can rearrange these to make that right triangle. And we know that the angle here is the same angle as our ramp. So that's 40 degrees between Fg and F perpendicular, which means if I want to find F perpendicular, that's the one that is adjacent to this angle. So we're going to use cosine because SOHCAHTOA, cosine is adjacent in the hypotenuse. So we end up with F perpendicular is FG times the cosine of theta. FG was 98.1, theta is 40. We get 75.1 newtons. Now this is only going to be your result if you are in degree mode in your calculator, so make sure that you're in the right mode. Radian mode would not calculate this appropriately because you're plugging in degrees here. To find the parallel force, that's the opposite of our angle of our 40 degrees. So parallel can be found by just doing F parallel is Fg times the sine of theta, which is 63.1. I added this 75.1 newtons to a separate free body diagram that we can build. Let's add this one as well, 63.1 newtons. Next we have R. If you remember, this block can only be sliding up and down. It's not accelerating out of the ramp or into the ramp based on the forces given. So R has to be equal and opposite to our perpendicular force. If you ever forget, like, is it parallel or is it perpendicular, just look at your picture. It's the one that has to stick out of the ramp, and that is opposite the 75.1 newtons. So 75.1 is also our total for R. So we are building this very nicely. The last force that we need is the force of friction that is going up the ramp in this case. And force of friction is simply found by using this equation. Now we save this for the last because we needed R in order to do this, and we needed F perpendicular in order to find R. So all of these are chained together, but now we know R, and now we still know this coefficient of friction is 0.15. Plugging those values in, we get a force of friction of 11.3 newtons. So looking at this picture, these do not all cancel out. We're going to get a net force, and you've actually seen this picture before. In our warm-up problem, it was exactly this scenario, and you were able to do it there. So you know how to take these last couple steps. Things will cancel out, and ultimately we got to 5.81. So let's see, 5.18. We can get to that same result here. We'll just do it one more time. These 75.1 cancel out. So our net force is just the difference between these parallel forces, and that gives you 51.8 newtons. And if you know the net force and you know the mass is 10 kilograms, F net 51.8 divided by 10 gets you 5.18 meters per second squared. All right, so that is a lot of steps. But as a reminder, none of these steps in itself are too challenging or too difficult. Probably the thing that I see people get wrong the most is finding these perpendicular and parallel components. So if you can do that and then look at your picture to know the relationships, the last couple steps are pretty straightforward. Now, this is going through that example if you knew the mass, but turns out you don't actually need to know the mass, which feels weird because all of these seem to be based on that calculation that you used with the mass. But if instead you were to try this problem without using mass at all, you can still do it. You just have to keep everything symbolic. So let's say that Fg, instead of plugging in numbers, is just mass times gravity. That means that F perpendicular being Fg times cosine of theta, we can just plug in that mg instead of Fg. So we have F perpendicular is just mg cosine of theta. Same thing. Oh, we can plug that in there. Same thing for our F perpendicular or F parallel. We end up with mg times the cosine or times the sine of theta. Then we knew that R was equal and opposite to this perpendicular force, and perpendicular force symbolically we said was mg cosine theta. So that is still the same. So notice we haven't plugged in any numbers. We're just keeping these symbols all the way through. And then our last force that we calculated was a force of friction. Force of friction was mu times R. But R was already symbolically calculated here as mg cosine theta. So that feels like a crazy long equation, but it's not that bad. It's mu, coefficient of friction, times what we already had solved for the perpendicular force, mg cosine theta. And we know that the net force is mass times acceleration. All right, looking at all of this together, we can make one equation to help us figure out what we're looking for. If you remember, we're looking for A, trying to find the acceleration here. And our net force can be determined as just being the difference between these two parallel forces, because the perpendiculars are both the same, mg cosine theta. That cancels out. So the difference between these two is just mg sine theta minus the coefficient of friction, mu, times mg cosine theta. Seems like a crazy equation, but that's what you did with the numbers. We just did it in smaller steps. So now if I plug in and rearrange this here, I can actually notice that mass shows up in every one of these terms. MA, mg, mg. I can divide everything by mass and get that out of there. And that leads me to A is equal to g sine theta times or minus mu times g cosine theta. So this is my equation to solve for A, and notice how mass isn't involved there at all. So if I wanted to try to solve that same problem that I did before, but not use 10 anywhere in it, all I need are these two values, this 40 degrees and this 0.15. So plugging in the things that I know, g is 9.81, theta is 40 degrees, and mu is 0.15. I can simplify that down a little bit, and I end up with an acceleration of 5.18 meters per second squared, which is exactly the same as what we found calculating all of those little parts. So I do expect that you can follow through this. Most cases that you're going to see ultimately will have a mass, so that's not a big issue. But there are scenarios in a problem like this, or in a problem like sliding to a stop on a horizontal surface, that you won't have a mass, and you might need to symbolically work through it until mass cancels out, because in a lot of cases mass does. So that leads us to our final takeaways. From this, you should be able to calculate the parallel and perpendicular components of the force due to gravity on a ramp. You should be able to calculate that force of friction required to keep an object in equilibrium. So know that friction will cancel out with that parallel force. You should be able to calculate the acceleration if there is not an equilibrium. So those forces don't cancel. Figure out what the acceleration resulting would be. And then what we did at the very last slide, you should be able to symbolically simplify a mathematical model until all the unnecessary information, like mass potentially, will cancel out, and you're able to solve something even though it doesn't look like you have enough numbers.